You're staring at your physics paper. You know the formulas, you memorize the textbook, yet when you get your paper back, you've somehow lost points on the exact topics you thought you mastered. Today, we're diving straight into decoding the Cambridge mark schemes for forces. We are completely skipping the fluff so you can maximize your exam score and stop leaking easy marks.
Right, let's just get into it. Ask yourself this. Why is it that you completely understand Hooke's law in class, you can picture a spring stretching, you even know the basic math, but you keep dropping points on the actual exam paper? What is the disconnect between your brain and the examiner's red pen?
Well, here's the painful reality. Simple, almost invisible mistakes, like missing units on substituted values or rounding numbers way too early in multi-step calculations, are silently destroying your grade. It's not that you don't know the physics. It's that you aren't playing the game by the examiner's strict mathematical rules. Standard revision tells you to just, read through syllabus sections 3.1 to 3.4. You see topics like turning effects, center of gravity, stretching and compressing. You might highlight it, read it twice, and think, okay, I'm ready. But passive reading completely fails to teach you the examiner's secret language. Reading the topics just doesn't show you where the invisible traps are laid out in that exam hall.
So it's time to embrace an anti-revision strategy. We need to stop merely rereading textbook chapters and start treating this test exactly like what it is, a puzzle with a highly predictable rubric. We need to decode what the exam board is actively looking for when they grade you.
Let's look at Hooke's law and moments, and specifically, the hidden traps.
Let's expose these traps. Notice how these aren't rare anomalies. These are the exact traps examiners set for spring constants and moments, usually right where students feel the most confident. Swapping load and extension on graph axes, it happens all the time. Giving vague explanations, that's a massive point killer. These traps transform what should literally be easy, guaranteed marks into a super frustrating loss.
You can see exactly how a flawed approach directly translates into harsh exam penalties. If your explanation is vague, you don't just get partial credit, you completely miss the scientific reasoning marks. If you make a graph axis error, you lose the gradient calculation marks because your math is now based on a totally inverted slope. And if you identify the wrong variables, your entire practical investigation answer is deemed a failure.
Which brings us to one of the most brutal phrases in the marking world: conclusions not supported by data. This exact phrase shows up constantly in examiner reports. And what it means is, your math might be perfectly right, your theory might be flawless, but your written conclusion completely ignored your own table of results. You have to connect your final statement directly back to the evidence you just generated.
So how do you actually guarantee top-band marks? In a moment, I'll show you the exact examiner clue that changes the answer completely. But first, you need the framework that makes that clue obvious.
Here's that framework. This four-step process is your ultimate tool for structuring high-mark answers across describe, explain, calculate, and evaluate questions. First, state the core concept, like Hooke's law. Second, pull hard evidence or data directly from the source material or table. Third, apply your scientific reasoning to link the data to the concept. And fourth, wrap it all up using specific examiner wording.
And what exactly do I mean by examiner wording? I mean utilizing precise Cambridge-approved terminology instead of generic conversational phrases. You must fulfill the command word requirements by speaking their exact language. Remember, the examiner isn't your friend chatting over coffee. They are looking for specific key words to check off on a rubric.
All right, let's jump into a quick interactive challenge. Spot the error.
Let's test your mark scheme thinking with a rapid pause and predict challenge. Notice how the flawed student answer is technically true. Yes, the spring got longer as the weight got heavier, but it's horribly vague. It earns 0 top-tier marks. Now look at the top band answer. Extension is directly proportional to load passing through origin. That secures full marks. It uses precise terminology like directly proportional. It correctly identifies extension and load, and it mentions the critical detail of passing through origin for the graph. That is exactly how you win.
Now for examiner feedback correction. Let's look at how to fix these issues.
Let's apply examiner-style corrections to your practical investigation skills. Because knowing the theory of moments or springs is really only half the battle. Knowing how to write about the experiment is where the A-stars are actually won. This is a direct insight from the source material. A strong answer must include correct terminology, the equation, and substituted values with units. The mark scheme explicitly rewards you for writing down the formula before you even begin to plug in your data. Never skip straight to the numbers. Formula, substitution, answer, units, every single time.
And if you're asked to design an experiment for a spring constant, you must proactively hit these essential setup variables. You need to mention the apparatus. You have to mention safety precautions, like wearing goggles in case the spring snaps under tension. You have to discuss your table design, how you'll choose graph scales, and most importantly, how you're going to handle uncertainties and anomalies.
This brilliantly illustrates the difference in practical answers. Never ever offer a weak practical improvement like "I would do it carefully" or "I would avoid human error." Honestly, those are immediate red flags for examiners. Instead, you want to explicitly state that you will improve reliability by repeating readings, calculating an average, and identifying any anomalies in the dataset.
Before you move to the next question on the exam, I want you to mentally run through this 4-point final answer check. Did you include final units? Did you use the correct significant figures? Is your graph scale linear? And is it taking up at least half the page? Did you account for uncertainty? Doing this quick mental check ensures you aren't leaving easy, guaranteed marks on the table.
Finally, let's talk about the missing practical skill. Okay, so you now know the framework to write the perfect answer. You know how to decode the language, state the equations, and avoid the most common math and graphing traps that catch out thousands of students every single year. But here is the ultimate stakes raiser. What happens when the examiner gives you a completely blank page and asks you to design the data analysis practical experiment from scratch? Because knowing the math won't save you if you can't construct the actual step-by-step investigation, define the independent and dependent variables, and structure the data table completely on your own.
That exact blank page data analysis setup is the next code layer you need to crack, and it is waiting for you in our next explainer. Click the video on your screen right now to master this crucial skill. And remember, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. Because if the examiner gave you a blank data table right now, would you actually know where to put the independent variable? Go find out right now.